Yes, we can see it. Perfect.
Okay. So thank you very much for the invitation, and all the talks were really very interesting. I'm learning a lot. So I would like to share with you our experience from 15 years of teaching computational biology in a PhD program jointly offered between Carnegie Mellon and the University of Pittsburgh, which we launched in 2004. It was the first joint program between the two universities. And we had to design all the courses from scratch. Of course, none of us got an education in computational biology, so we had to come up with new concepts, new courses. And we were very lucky to be founded even before we launched the program, for designing the program actually, by HHMI. And now it has been 15 years, hard to believe. So the first question we asked then was, what skills are essential for computational biologists? And you can find these answers to those questions easily, you know, by this software. You see evolution, genomics, modeling, mathematical science, or biochemistry. And then the fact that it's an interdisciplinary topic and foundations are very important. I agree with Alex. And then we also realized that in recent years, US life and health science PhDs have been increasingly employed by the private sector, while the positions in academia have been decreasing. So we have to think, we have to customize our program to respond to this growing need we thought. And again, more recently, when you do this type of searches, you see what is at the very center. And this is not by design, this is what happens. It's data at the center, and then machine learning. And so these are, so our program is bi-institutional, so it's two institutions. Kara mentioned the number, as the number of institutions increases, there's a decrease in productivity, but we think it is, 2 was a good number, because we took advantage of the strength of Carnegie Mellon in computer science, and also strength of the University of Pittsburgh in medical sciences. And we wanted to have a program that would be training students from computer science, life science, physical sciences. Shared leadership, shared curriculum, and shared activities. Everything would be very well integrated. So the close proximity of the two universities actually in Pittsburgh helped us a lot. You can see how these are geographically located. And also, what are the courses? We thought we should have 3 core courses then. So of those 3 core courses, you can see the cell and systems modeling, computational genomics, and computational structural biology to cover those 3 areas. But then we thought there is a need for a very strong machine learning background to be able to solve not only current problems, but problems of the future. And what was also unique to our program is we have a required laboratory course for our students. They go once a week to a lab, they do experiments, and this was designed actually with the support from HHMI. So this is the required part. And then we realized that actually there is a need for student, customizing the courses to the need of the students. So we designed life science, for example. Drug discovery became a very important course. Personalized medicine is another. And then, of course, there is what one doesn't learn in a traditional classroom, or how to be scientists type of questions, including scientific ethics. And as also mentioned earlier, our students are very interdisciplinary. We have students from a variety of background: biology, engineering, neuroscience, mathematics, etc. And of course, this comes with a challenge. So they don't have, not all of them have all the skills to respond to different needs, and they may not have sufficient background interest. So to answer a question that you raised, Philip, we wanted to see which students perform well in which courses, or the other way around, which students did not perform well in which courses. Okay, so this is the statistics from machine learning course. which we would expect to be really very good for computer scientists, computer science and computational biology background students. And that was true. The majority of the students who got a B- or less were from biological science, biochemistry, and even mathematics, physics, and engineering. But then when we look at the students in the cell and systems modeling, to our surprise, so eliminating the 1%, we see three major groups: computational biologists and computer science background. These two amount to almost 2/3 of the students who didn't do well. So there was a problem that we perceived when it comes to modeling. So engineering and physical science students did better in modeling. And then when we looked at the laboratory course, which you would expect, of course, computational, computer science, math, and biochemistry, we were surprised to see biochemistry here. But again, computer science and math, they didn't do well. So in summary, in those two core courses, which are very important, we were disappointed to see that those coming from computer science and math background amounted to 2/3 of students who did not do well. This is a little bit what Alex also said. It is a bit harder for this group of students to understand, have insights into the biological problems, apparently. Amazingly, in computational genomics, there was quite a balance between the different groups. And as you might expect, in computational structural biology, the computer science students did not do well. Again, as well as mathematics. You can see almost 70% of the students who didn't receive a good score were from computer science or mathematics. So that, then we learn from that, right? We learn and we customize our requirements and our lessons, courses. So we started to seek now in our applicants some experience in biological research. We wanted them to come with some background, and currently, some of them have a mathematics master's degree, an average of 11 months of research experience they have. And then, since we saw that mathematics or computational skills was not a problem, we also started to lower those expectations at the admissions. And we also realized that, only undergraduate studies are not enough for our students to be well prepared for our program. So we changed the curriculum to have more flexibility, to let them, of course, take remedial courses, but then more coursework would cut into the research time. There were peer tutoring, reduction in course requirements. We had to readjust. And it helped. The number of students, the number of applicants we have grew from 94 to 325 during this 13-year period. And then we had more and more domestic US applicants. GPA and GRE numbers, we came to the conclusion that they don't mean much. All of them have high GRE scores. What matters more is the interest and the passion. If they have some research experience and strong desire, that was more important. The completion rate in our program is about 90%. The mean graduation time is 5.5 years, and all our students, on average, they have 3 papers, 1 or 2 as first authors. What we are very proud of is that 80% of our graduates remain in research-related or intensive positions, not necessarily in academia, but it could be equally, postdoctoral positions or high-level positions in industry, actually. So we reached the conclusion that prior exposure to some research is important to excel in our program, and these individuals would be great assets to their labs. It is possible to provide a rigorous training in 4 or 5 years. Our goal was 4, but now it is 5 perhaps. And there is a need to start training earlier than doctoral studies. So toward this goal, we have been partnering with many undergraduate or summer programs. So for example, we have an REU program at the same time, and we offer many new courses, as you can see here. We have been partnering with alumni, with industry. Here is our tech bio program, training and experimentation in computational biology, which has been founded since 2002. And those students actually are really, this summer program of 10 weeks is already good enough for them to understand what is needed, or whether they want to pursue that direction of a career. High school program, we got the R25 funded high school program, and we are very proud to say that 50% of our high school students are from underrepresented minority groups. And as to the RU program, undergraduate research education, again, we have 43% from underrepresented groups, 54% from non-PhD granting schools, and look at that, 85% of them go to graduate school or work in STEM. They're coming from non-PhD granting schools, and they do that. So we are very happy that it is possible to, when they are younger. This is one of the stellar students I had personally. We gave her an admission to our program. She rejected our offer. She went to Johns Hopkins to do computational biology. We are very proud of her. So Joe Ayub has been behind all this, training tomorrow's scientists. They designed their t-shirts each summer. This is a big project. And of course, we started also a master's program, realizing that there is a need for education at lower levels. So some measures of success would be the fact that our alumni are in high demand for excellent research positions, as well as competitive industry positions. And you can see a few here. And interestingly, they are even being hired to senior positions. Some of them just skip the postdoctoral studies, they become assistant professors. Yet we still have challenges. There is no standard student. We need to adapt to a heterogeneous group. Even the well-trained, supposedly well-trained students, they can struggle with the interdisciplinary material. And now we are also competing with many companies which offer non-research positions. So 20% of our students, which is a considerable fraction, they go to those companies. I already have 2 PhD students who work for Google right now. So gender diversity in our area has been a problem. We have, as well as the underrepresented minorities. As I said, we did very well in the undergraduate and high school program, but not in our doctoral program. We have only 7.5% of URMs. And as to the composition of our students, okay, half of them are from the United States, but even the international students are not diverse enough to my standard. And in terms of gender diversity, right now we have, our average is 30 to 70. But those, our graduates were almost 20 to 80, and those currently in the program are almost 40 to 60. So that shows that we made a progress, from 80 to 60, actually, in the current students. So one other thing we wanted to learn is, since we're going to train students for industry, and that's one of the purposes, right? We wanted to understand what are the needs, and we started a survey and asked many questions. And we wanted to get feedback and try to understand what are the most important areas. First of all, one question was, is there a demand for master's level programs? Because before we started our computational biology master's program, we wanted to know that. And this is the distribution of answers. So 33% of those companies, they said yes, and they do hire them. 25% they said yes again, but they can't find easily such people. So that gave us a lot of confidence to start this computational biology master's program. 25% said, oh, we prefer PhD students. 8.3 didn't know what to say. They had no answer. But overall, we came to the conclusion that yes, there is a need in industry, a demand for master's level students, not necessarily PhD, because some of the tasks could be accomplished by them. And then we also asked the folks from industry, what are the technical skills that you think are essential for computational biologists? And I have to say, we were very disappointed. Look at the answers. They start exact. They need to know exact, linear regression, or they need to do data analysis, statistics, machine learning. So it was very heavily computational. There is But then some of them start to say maybe some knowledge of molecular biology, or then both biology and computations. So increasingly so there is quite a big need. My understanding is for data analysis, big data processing and version optimization, etc. But some also realize, my favorite is this one, working directly with experimental biologists, understanding experiments to be able to guide and design the lab work. And that's what actually we try to accomplish in our program. We want our students to be able to talk from people from different disciplines and not only interpret data, but to be able to give feedback and hypotheses for new design. And then we said, okay, are you interested in accepting interns? Because we thought this would be an important part of our program. And then they said 42% yes. They said yes. 33, they said no. And 25, they didn't know. Maybe, they said. So that's not very encouraging. My view is we need really stronger ties, partnerships with industry, and perhaps prove to them how our students can be really useful to their research through those internship programs. So that concludes my talk. I would like to thank all of you for listening. This is a photo from last year. And here we have, what I would like to show here is a network. The names which you can't see are faculty members in our program. Blue is University of Pittsburgh, red is Carnegie Mellon. And these are how we have been working together, networking for mentoring our students, and how this program helped us initiate, launch interdisciplinary efforts between different labs. The best way of launching a collaboration is probably co-mentoring a student, which we have done very extensively in our program. So I'm hoping that we will have such a diagram next time with industry when I will present. And thank you very much for your attention.
Well, thank you for a really great talk. There's actually a couple of questions that are in the panelist chat, and I want to call out one of them because you just gave, I think, really important advice for people that are building or engaged in training programs from a faculty perspective. But I guess the other question, based on what I think is a very substantial amount of experience that you have, is what are the top 1 or 2 pieces of advice you would give to the trainees in the audience today in terms of launching their careers as well, building on these types of training opportunities?
So, I would advise them to take advantage of any opportunity to prepare themselves. Again, some kind of summer research experience or some research experience before coming to this type of program, it makes a big difference. We have realized that this is one of the major determinants of success. And probably those individuals are already very interested, very involved, and that's the reason. But we have had even students from English literature. She did very well. But it is better to start to familiarize with those topics early on during preferably undergraduate studies, if not high school.
That's very helpful. There's another question which I will ask you to answer in the Q&A session or via chat, just so other people can see the answers. But again, thanks.